MPhil. Yes.
Which class is this? Is it a database? Friends, friends, price, price. You know, we practice the thing by this time. Frank, you know, we practice the thing by this time. You know, we practice the thing by this time. Staying back, you will do classes. Jimmy. What's wrong with this class? Prof, you're welcome.
Oh, thank you very much. You are already in class. It's not yet time. It's one minute to time, and you are already here.
Yeah,
Yeah, that's
I'm,
right.
I'm,
So how are you?
I'm putting up European life.
That's very good. That's the best.
Yes, yes.
That's the best. Sure. We just wait for a moment, allowing others to join, and we get started.
Okay, Prof.
Okay. Okay, then good evening, everybody. I hope you can hear me loud and clear.
Yes, we can hear you.
That's right. That's right. Okay. We are back to class. And when we met last week, we covered a topic on transaction management. And as you can see from the slide I'm sharing with you, I hope you can view the slide from your end.
Yes, we can see it.
You see, last week we discussed chapter 20, which is on transaction management. We highlighted a lot of key issues in there, and the chapter is regarded as being fully covered. The rest is left with you to go and read the chapter. Now, on our course outline, we are going to treat query processing and query optimization, but we'll not deal with that today. To be part of our subsequent lectures. So we will jump over query processing. Today we will go straight to parallel databases, and we would delve into chapter 22. A lot of things there that will be of critical importance to us. I'm going to use another document to teach this, but you are supposed to read chapter 22 as well as chapter 24. So today's class will center on these two chapters. They are seriously very easy reading and very interesting topics that we are coming to treat. So having said so, I would go straight to today's lecture. But as usual, anytime we come, even before the lecture starts, I ask whether there are some challenges, comments, or something you want to share with the class, or maybe something is not going well, and then you want to bring it to the attention of the lecturer. If there is anything like that, feel free and let me know. If there is nothing, then thank God we can move on with what we want to learn today. But before I start the class and begin to talk about parallel databases and distributed databases, I want to hear from you how things are going. Are you coping very well with the courses that you are doing, or there are some challenges? Can we say that all is well, or that there are some challenges that you are facing, or the class is facing in general? Okay. So far as I don't receive any response, it means all is well. Is that not the meaning?
No, Prof.
So all
So,
is
Prof, people
Generally,
may not
there will
joining.
be challenges.
pardon?
Generally, there will be challenges, but uh, uh, we are programmed to face those challenges.
Okay, that's right. Okay. All right. Since you have been programmed to face the challenges, know that you are doing computer science. As a computer science student, you have to be programmed so that the programs can execute and solve the
Nobody
problems.
force us into
That's interesting.
it.
Okay. All right. Having said so, let's move on to today's lecture. As you can see from this Word document that I'm sharing with you, today's lecture will center on parallel databases and then distributed databases. Of course, it will involve also data replication methods and then so forth. So we would be looking at these objectives. Of course, introduction, the architecture of parallel databases, input, output, parallelism, interquery, intra-query, interoperation parallelism, design issues in parallel systems, then distributed database systems, then the architecture of distributed database systems. So this and many more are what we are coming to discuss under this topic. Okay. By way of introduction, when we studied transactions the other day, we were saying that transactions are normally useful when we come to multi-user environments where several users may have access to the same data object. Okay. Now, parallelism indicates that several processes can process a set of instructions concurrently, and at the end they put their results together and then probably save them back to disk. The concept of parallel databases came as a result of a number of things. One, prices of microprocessors, memory, and even disk have dropped significantly. In the past, to buy even a cheap memory card and so on, they were quite expensive. Even a disk was very expensive. But these days, these things are quite not expensive. Of course, in our part of the world, it still appears to be expensive, and it doesn't look like the prices are dropping. But the other parts of the world, prices of computing devices are dropping, not increasing, dropping. But because of our currency, it appears they are increasing, but no, they are rather dropping. Okay. Now, even to the extent that these days, even desktop computers have multiple processors in them, even handheld devices now having multiple processors in them. So once we can have multiple processors in a device or a computer, then we should be able to augment the use of these processors such that we don't say one processor could process a transaction or a set of instructions alone. We could schedule processors in such a manner that maybe 10 processors can work on one transaction. So if we have a set of 10 lines forming a transaction, we can allow 10 processors to do it. In that case, if we have 10 lines and 10 processors or CPUs, maybe we can distribute it in such a manner that maybe the processor one take line, the first line of the codes and execute it. Processor 2, processor 3, and then so forth. So if we do it that way, then the throughput, turnaround time, performance will increase, because if one processor does the 10 lines compared with 10 processors doing the same 10 lines, then performance will be enhanced. Okay, so there is all the concept of parallel processing. Since machines are now being installed with multiple processors, memory, disk, multiple disks, and so forth, then databases also, developers of databases also begin to look at how can we make our systems such that several processors can access objects within the database and process them concurrently. And in fact, the kind of volumes of data that we generate these days, or we put on disk these days, are very huge. So if we don't have a situation where you have processes that can handle large volumes of transactions at the same time, then you can imagine that queries may take maybe hours or even lifetime to execute or to complete their execution, or years to do that. So parallel machines with several microprocessors and so forth, and databases also lend themselves to the fact that machines or processors can handle large volumes of data, even to an extent that even multimedia objects, images, and so forth are being generated. Large volumes are being generated every day. Even individuals like all of us over here, you can estimate even the amount of data you generate a day. When you take pictures, send messages, receive messages, and then transact business and even voice calls, all these. So individuals generate large volumes of data. If you want to process this data, and then we have to use the the conventional way of processing such data, it will become a problem. So databases are now, as they are storing large volumes of data, people are using such data to do, results of such data to do several things. And then having in mind that we need to provide high throughput for such transactions with huge data, parallel processing becomes critically important. Okay, so that's the way, by way of introduction. So now let's take a look at parallelism in databases. How do we carry out parallel processing when it comes to databases? We'll be looking at various techniques very soon, but just for the way of having an idea as to how these things are done, we can look at some issues here. So when we have disk or multiple disk and data on multiple disk, or data on even one disk, can be partitioned. For instance, if you have data, we can partition the data even across multiple disks for parallel read and write. So we move some aspect of the data to one disk, another to another disk. So we distribute the data across disk. Now, we can also do it this way. As we distribute the data across disk for processing, we can also distribute the operations. You see, when we look at a query, a SQL statement, there are various segments within it that form the query statement. So we have sort, we can say order by, or join, or aggregation, something like you want to sum, count, average, and other statistical functions. So you see that individual queries in themselves are formulated with various segments. So once we have identified segments within a query, then we could see that queries, segments of the segments within the query could be processed by different processes. Okay, so having that in mind also, that queries can be segregated and then be processed even by different processes. As we partition the data even across various disks, we can also go down to execute queries based on segments. So in that case, apart from the fact that a query could do that, also data partition across various disks. So we can ask processor 1 to go and process the data on disk 1. Then processor 2 process the data on disk, and then so forth and so forth. Okay. You also notice that when situations of this occur, there is a problem can crop up. Maybe I should ask you, if several query processes are executing queries. Let's say 10 queries, example that we gave earlier, 10 queries. Each processor goes to pick one line and 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 processes it. And then at the end of the day, they put their results together. What challenge do you think need to be addressed before such a thing can work well? Anybody? If you don't respond, I'll mention your name.
Hello, Prof.
Yes.
Please, can we say we should look at dirty reading? Like
Okay.
it, okay.
Yes. So, yes. So what you want to say is there will be problem with these concurrency issues that we discussed the other day. Because one processor, another processor may go and read dirty data. So you will see that this topic is related to what we did last week. So Gift, you are right. Gift, I'm going to give you plenty marks. So
Thank you, Jay.
Gift is topping the class already. Oh.
No, we were about to answer her because she's a lady. We give her the chance.
Okay, I will tell you something before we continue. When I was doing my masters, and it will interest you, I did my masters in China several years ago, 1997. 1997, I did my masters in China. So when we got there and we started classes, of course, the class was conducted in English. Yeah. I made up my mind. Of course, I knew myself that I would take it easy, and I knew I would do well. So when we attend classes, and then they sometimes ask questions, I'll be quiet. And there was one lady from Uganda who will be answering the questions or attempting to be answering the questions. When they give homework every week. It's like the way Americans do it. They ask you to do a lot of homework. I wasn't really enthusiastic about this homework thing, even though I will do and submit. And not knowing that we have two different systems. Their system, they pay more attention to class participation and then homeworks and all that, but not the final exam. Me, I was preparing the final exam, I'm going to blow the paper. It came to the final exam. I really blew. I did so well in the exam, but when the grades came, I was very sad because I thought I was going to have A, and I didn't have A. Only to understand that over there, the interest is not about final exam. The interest is about your participation in class. And Americans also do the same. So the lady who, of course, in my view, are more intelligent than her, had A in that paper. It was some statistics and some mathematics, I think numerical methods. He had A in that paper, whilst I believe I knew the content more than her because of her participation in class. So please, here we are not using American method. Otherwise, if we were using strictly American method, Gifty will have taken all the marks away. That's by the way. Let's continue. Okay, so, but because I schooled in China and the US as well, that's why I'm also giving some marks for class participation. Okay, having said so, concurrency, when you think about these parallel databases and parallel processing and so forth, immediately you have to be worried about concurrency. But thank God the issues regarding concurrency were discussed the other day, where solutions regarding locking and time stamping and so forth were discussed. And there are many protocols such as two-phase. We even have three-phase protocols and all that could handle concurrency. Okay. What are the main goals of parallel databases? Of course, improve performance. System performance can be improved by connecting multiple CPUs and disk in parallel. All right. Even improve availability of data. So data can be copied to multiple locations to improve its availability, because we are coming to partition data. So if we split data and spread it across multiple disks, data gets available quickly. You even see sometimes you want to download maybe some files or content, then it will ask you to choose some selected mirrored files close to you or whatever, because the content has been distributed across the globe. So perhaps downloading from a certain site will improve the availability and then even the speed and so forth. Now also improve reliability. The system reliability is improved with completeness, accuracy, and data availability. It provides distributed access to data. Companies do that a lot. So you will see a big global company will distribute this data across the globe. The data distributed across the globe could be processed by several processors also across the globe. But because the data is distributed, access to data becomes quite easier. Okay. To continue, let us take a look at this diagram. Now, if you should count the number of major components in this diagram, how many main components can you see in this diagram? Anybody? Look at it carefully and tell me the number of components you can see. Yes. Emanuela, are you there? I want the lady's voice again. Emanuela is not there. The machine is on, but he's not with it. Okay, Eric Ofori. Eric is also not there, even though it is assumed that she is here. Bright, John Bright.
Prof.
Yes.
So I can see 5 components.
You can see 5.
Yes.
What are they?
First, I can see the computers. I can see the communication channel.
Mm-hmm.
I can see the data storage.
Mm-hmm.
I can see the processor. And I can see the memory.
Okay, you are very right. There are 5 components over here. Yeah, you are very right. Computers, communication channel, processor, memory, and storage. Okay, so let's bear this in our minds because that is what is coming to help us explain the types of parallel database architectures. So, in fact, for a computer, if we have processor, memory, data storage, these three things interact. They interact, and then the users also interface these key components, and then users may interface these components through a network sort of or communication channel. So having this in mind, let us discuss different types of uh, parallel database architectures. We have various types, but the major ones are four. So we have shared memory system. This is an architecture for parallel databases, shared memory system. So immediately you hear shared memory. Let me just find out when you say shared, what is sharing the memory? When you say shared memory, which of the components that we saw in the diagram sharing the memory? This class appears to be very quiet today. What is the problem?
You see the storage, the laptop.
No. The components that we mentioned over there, the five components that we mentioned, one of them is memory. And I'm asking, when we say shared memory, which of the components is sharing the memory?
The database.
Okay, you've made an attempt. Now, Esther Ama Mensa, are you there?
The processor.
Why is it that several students switch on the device, but they are not there? When I even mention their names, they don't respond. Okay. Okay, Alicia.
So is it the intercommunication channel?
Oh, no. Actually, is the processor. Is the processor sharing the memory? The processor sharing the memory. Okay, so let's go back and understand what it means by shared memory. The shared memory system uses multiple processors attached to global shared memory through communication channel. So you will see there are processors, several processors, CPUs, are attached to one common or a global memory, and they do so through communication channel. Okay, so that is the definition of shared memory architecture. When you can, even when you take a look at this diagram, you see we have three processes. Communication net channel is in between. Then we have the global memory. So for processes to have access to the memory, they will pass through a network. to a global memory. Interestingly, they all share the same memory. So some large amount of memory is available to all the processes. You can also see that the memory is attached to several disks. So you see the processor can, through the network, access the shared memory, process the data, could save to any of the disk. After the data is processed, you can save to disk 1, disk 2, disk 3, or any of the disks so easily. So this is the diagram that shows the architecture of shared memory. So the shared memory system or systems have large amount of cache memory at each processor. So frequent referencing to the shared memory is avoided. You will see that when processor works, it visits the memory frequently. But in this case, even though the diagram has not shown it, each processor has cache memory attached to it. So processor 1 has a cache memory attached to it. Processor 2 has cache memory attached to it, and so forth, and so forth. Okay. So because they have individual cache memories attached to them or to each processor, anytime some information needs to be fetched from global memory, and that information is currently already in the cache memory, there will be no need to have to access the global memory again through the communication networks. By so doing, the process as a whole becomes more efficient and improves performance. So if a processor even performs a write operation to local memory, maybe I should ask you this question. If one processor now processes some data and it writes it to the local cache memory, what do you think needs to be done before processor 2 will be able to have access to that data? Maybe processor 2 needs that data. What should be done before processor 2 should be able to have access to what is kept in the cache memory of processor 1? Anybody's idea? Yes. Sadiq, are you here? Okay. Ofori Prince, are you here? It looks as if I only have few students in class today. I'm going to take
Hello, Prof.
You switch on the machine and then you don't listen to the discussion going on. Sadiq.
Hello, Prof.
You switch on your device and then you are not listening to what I'm discussing with you.
Prof, I'm following.
You are following, eh? Okay, then that's right. That's right.
Yes, please. I'm following.
You are, since you are following, you are coming to answer this question because you are following. Okay, the question is
All right,
because
Prof.
each processor has with it a cache memory, a local cache memory, where it can read and even write data into. If a processor 1 writes some data into the cache, that's the local memory, processor 2 needs that data. How will processor 2 be able to have access to the data written to the cache memory of processor 1? In your view, what do you think will be done, or how we can have access? Okay, since Sadiq is unable to answer the question, any other person can help.
Prof, since
Go ahead.
Prof.
Uh-huh.
Yeah, I believe that whatever is in the cache must be committed to the global memory first before the other processor will be able to access the information.
Who has answered that question? Who has just spoken? Okay,
Prof,
Kofi Ofuru.
since they said this. Hello, Prof. Since they said they shared a global memory, each processor can access a data written by the other processor.
But this time around, the data is written to the cache memory, local memory, but not on the global memory. Okay, a solution has been provided from one of you that all that is needed is that the local processor will have to update the global memory with what has been written to its cache before processor 2 will be able to have access to that current or updated information. Okay, there are some advantages to this architecture. The first one is the fact that data is easily accessible to any processor. Because they all share the same memory, data is accessible, very easily accessible to all of them. And one processor can send message to the other processors more efficiently because they share the same memory. So sending data to or information or message to the other is just, it can be done more efficiently. Okay, but there are some challenges that we should also foresee. Look at this diagram carefully and tell me, what do you think will be one of the major challenges to this architecture? What should be the major challenge to this architecture?
Prof, please.
Okay, go ahead. Mm-hmm.
Latency and synchronization of all devices present.
What will cause the latency in your
The
view?
fact that information needs to be communicated across various nodes, like from the processor to the global memory to the disk and then back.
Okay. Yeah, you make an attempt, but I expect you to mention a component that could be creating the bottleneck when you look on the diagram. In between the processor and the global memory, we have what?
Prof, when there's latency in the network.
The network, okay. So you see the intercommunication network can create a bottleneck between the processor and then the memory. So that's one of the problems. So the waiting time of processes is increased due to the number of processes as well. The communication channel can cause a problem, even bandwidth problem. Anytime a processor wants to visit the memory, it has to pass through a intercommunication channel. That
Prof,
alone,
can we
bandwidth.
see scalability issues? Scalability.
Okay, in what sense?
When the number of processes increase, can cause scalability
So
limitation.
you are right. If you increase the number of processes, then correspondingly you should be increasing the channel as well. Otherwise, all the processes will compete for the same limited channel, so they can create problems until you increase the capacity of the intercommunication channel, and you just keep increasing the processes, then there will be the problem you are talking about. So there can be a number of issues with this architecture.
Prof,
Okay. Yes.
Hello, Prof.
please,
Mhm.
I'm just thinking, would there be issues of
Yeah, hello,
data
Prof. So,
replication or redundancy? Because all like data from the various processes have to save across board, or in all this to have synchronization. I'm thinking there will be issues of redundancy. I don't know.
Or to bring the redundancy.
Replication of data.
When we come to distributed databases, is the replication of data that we actually even want to. Unlike relational database, where we say that we should remove redundancy, when we come to issues of having to do with distributed databases, the redundancy is even permitted, because the idea is to make data easily available to the use. So at the tail end, you say we are even going to talk about replication, where you even duplicate data from one site to another site. Then you keep duplicating data from one location to another location. Though it's a problem when we come to the distributed databases, because we want to achieve other objectives, data replication, so to speak, sometimes redundancy, because you make the same copy to another machine, another server somewhere, is even allowed. Okay. And there is a lady who wants to talk. Is it gifted again?
hello, Prof. This is Emanuela. Yes,
Emanuela,
so,
when you weren't available. Okay,
Prof,
continue.
please, I was in a car. Sorry. So I was
Okay.
asking about in the case of scaling, where we said we would increase the number of processes, would it also affect the disk spaces, in the sense that would we need additional disk space?
If the disk
Or
spaces
to the
are
various processes?
not necessarily true, but if the disk spaces are not large enough to store the data that the processes will be dealing with, then of course you must increase the disk sizes as well, or add more disk. But if the
Prof.
disk spaces are enough for the processes, then that shouldn't be a problem.
Okay, Prof,
Okay.
please, I have a question.
Okay. Go ahead.
Please, when you asked about the cache, how other processors will be able to access information from the cache, I wanted to. One person said when the cache data is stored in the local memory, that is the only time another processor can access the cache, access that information. I wanted to confirm.
Nobody said so. Nobody said so. What the person said is the data in the cache memory or local cache memory of a processor have to be written to the global memory before the other processor will be able to have access to it.
Okay.
I think that's what the person said. That if the person said it that way, then it is wrong. Then the issue is it must write it to the global cache before other processors will have access to it.
Okay. Okay, sir.
Okay. Having said so, now we raised a number of issues and challenges with this. Now we can then look at another architecture. If the first architecture is shared disk, shared memory, then the next one will be shared disk. If you even see the first diagram where we have processor linked to memory and linked to data, processor sharing memory, now processor sharing what? Disk, which is data storage. So the next architecture is shared disk system. In this system, multiple processors now accesses multiple disks, and they do so through the same intercommunication channel. You see, in this case, instead of each processor having cache memories, of course they still have anyway, they actually have the local memory. They have their own memory. Okay, so each, as you can see in the diagram, each of the three processors that we have, they are having their own memory, random access memory attached to it. What they actually share or have in common is the communication network through which they access the disk. So the three disks over here can be accessed by any of the processors. So processor 1 can write to disk 1, disk 2, disk 3. Similarly, processor 3 can also do the same. So in this case, you see that they are sharing the disk. So assuming that we have various locations. Processor 1 is located somewhere in one country, processor 2 another country, processor 3 another country. Then we have internet or whatever, or network in between them, or specific network in between them. Then we distribute the disk also across many locations. So processor 1 will have access to any of the disk. So even we have, let's say, processor 1 in Afghanistan, and then processor 2 in Iraq, processor 3 in Kuwait. You see that each of them can process some data and then can save to disk 1, disk 2, disk 3. In that case, it makes the data available across all the disks immediately. Processor 2 can, which is in Afghanistan, can also see what has been done, fetch the data from any of the disks, brings it to its local memory, process it, and then save to maybe one disk or two or even all. You can search data from any of the disks. So this architecture looks quite good because we can deal with data across everywhere, across the globe. Okay, having said so, what are its advantages? One of the key advantages with shared disk is fault tolerance. Fault. That means it can tolerate fault. What does it mean? If one processor and its memory fails, the other processors can complete the task. So even if they are processing data in parallel, some are doing a portion of it, others are doing a portion. Even if one memory and processor fails, the other two processors can continue and complete the task because they can save to disk, they can have access to all the disks and so on, so they can complete the task. So that is one of the major advantages to this architecture. But it has other advantages you can also think of. But there are some disadvantages to it as well. The shared disk system has limited scalability as large amount of data travels across the interconnectivity network, because this time around, in fact, the amount of data that are supposed to be fetched from disk through the network to local memory, process, push data through the network. So if these processes are dealing with large volumes of data, and data is fetched to the local memory, handled at that point, and then saved back, I'm afraid then your network bandwidth must be high, because data that traverses disk to processor and so can be huge. Okay, so that is one of the issues that we have with this kind of architecture. We mentioned something similar earlier. If you begin to add more processes, then the system will slow down until, of course, if you add more processes, then you must increase the bandwidth or the network capacity. But not even that, even the disk access, you know that these architectures cannot work without this concurrency and others put in place. Otherwise, some will be reading dirty data and then so forth. So concurrency integrated into this. So for the moment you are adding more processes and all that, you will need to struggle with the system being slowed down, because there will be, as we learned the other time, even to deal with what do we call it? To deal with concurrency, where one transaction may be asked to wait, and then and so forth. So adding more processes and then so forth, then we are going to have an issue with the system slowing down. Okay, can anybody think about any other challenge that this architecture can face? Okay. Now, Oracle. This is the architecture that Oracle has implemented. So Oracle systems use this architecture. Okay. Now the third, if you look at the very first diagram that we have, there are only two components that can be shared. You have memory and data storage. So the processor will share memory and share the data storage on disk. What else can it share? Nothing, because these are the main components. So we have another architecture we call shared nothing. Shared, it means I don't share disk, don't share processor. Shared nothing architecture. In that architecture, the processor is sharing nothing or not sharing anything with the other directly. So the processor has its own local memory and its own local disk. So as you can see from here, processor 1 has its own memory and disk. Processor 2, its own memory and disk. Processor 3, and so forth. The only thing that appears that they can communicate, or through which they can communicate among themselves, is the communication channel. So the processors can communicate with each other through the intercommunication channels. Okay, this architecture is extremely common. Extremely common. Maybe somebody can throw some light into this architecture, how common or where he has seen one before. So anybody who can tell us where he has ever seen one of these architectures can let us know. Any idea? Some of these things, don't be thinking that they are in the textbook, they are far away from you. This architecture is right with you. Can you give me an example of this shared nothing architecture?
Prof,
Yes, go ahead.
see the standalone computers.
Okay, we will know if we say standalone, it sounds like we are not connected to any network, but I understand what you want to do. Every machines, any computer on its own. So servers, even your laptop that you are having there is this kind of architecture. Servers that we have at workplaces, computers on their own connected to any network. You see, that's a kind of architecture we are even using here. My machine can act as a server on its own, having its own memory and its own disk processor. But then we can communicate. I'm communicating with your device or your computer through communication channel. So this architecture is all over the place. Workplaces, you see that they just go and buy a server. Then the server comes with processor, memory, and disk on its own. Another one comes with it. So all they need to do is to plug it to a network. Once they are plugged to a network, you will see that one machine can access even the one machine can access the other machine. They can only do so through intercommunication channels. So this is all over, and that's what we've been using everywhere. Now, even with your laptop connected through a network to reach another network, it is this. Machines are on their machines have all the things on their own processor, memory, and disk. Another machine processor and disk, and so forth and so forth. Having said so, any of the machines on the network can act as a server to serve the data which is stored on local disk. So processor 1 can even serve others with its data through the communication networks. You can even copy data from one machine to the other so easily across the network. Okay, but what are the advantages of this architecture? A number of processes and disks can be connected as per the requirements in the shared nothing system. This one is so easy. If your organization feels that we need one more server, all they need to do is to just go and buy the server and then they plug it to the network, maybe through Cat6 or any or wireless or cable or whatever channel they want. It's a matter of just buying one machine and then plug it to the network. There you are working. It's not complex at all. Shared nothing system can support many processes, which makes the system more scalable. So you can scale the system as much as possible, but then bearing in mind the availability or the capacity of the intercommunication channel. The disadvantage here is data partitioning is required. Here we need data partitioning because they don't share common disk. They don't share common disk where we can say that our processes can visit one disk and so on. So we will need to partition data in such a manner that we can distribute this data across the disk. The cost of communication for accessing local disk is also high. So if processor 1 wants to access processor 2, the cost of doing that is high because they are not sharing the common disk. So to have access to that may be higher. Okay, having said so, I want somebody to suggest the fourth or the name or describe in brief how you or she thinks the last architecture will be like. Now we discuss shared memory, shared disk, shared nothing. The fourth one, what do you think it will be? If you want to get
Shared everything.
shared everything.
Shared. Yes.
Because they shared nothing, now they have to share everything. Is that not it? Okay,
Yes, sir.
shared everything. So how do you, if you want to put it in a more technical language, how will it sound like? Okay, so that is the hybrid, is that not it? Some kind
Yes,
of
Doc.
hybrid. Yes, hybrid. So
Yes.
you are right. Shared everything. That's hybrid. We call it hierarchical system or non-uniform memory architecture. So this hierarchical model is a hybrid of shared memory, shared disk, and shared nothing. So the architecture looks like this, but you can even draw it better. So where a portion of the diagram will be shared nothing, a portion will be shared disk, a portion will be shared memory, and then there are interconnectivities among them. So in this system, each group of processes has local memory. Once they have local memory, that is a shared disk. But processes from other groups can access memory which is associated with the other groups. So the diagram looks similar like this. So all the three diagrams that we saw could be put into one diagram. The advantage of this could be obvious. It will improve scalability of the system. Then memory bottlenecks or shortage of memory problem will be minimized. But the disadvantage is the cost of building architecture that has to integrate all the other architectures. So that is the disadvantage of the hierarchical system or hierarchical model. Okay. Now we have discussed the four major architectures of parallel databases. We would be talking next about the how data is partitioned.
Prof,
Yes.
I'm sorry, but I was looking through the book and I didn't see the hybrid bit. I only saw shared memory, shared disk, and shared nothing. And the non-uniform one was not stated.
Okay. But it is there. So if it is not in the book, you can add this one. You can add this one to it. Is that okay?
Yeah, that's fine. That is
No,
provided you
no,
make
no.
the made
Yes. No,
available.
no, no. Yeah, I'll make this slide available. I'll make the slide available. Okay. Any other question? We are moving away from the architecture and we are coming down to now to the strategies, partitioning strategies. Michael, is your hand up? Michael Sedinam.
No, please, my hand is not up.
Then you should lower it too. I can see your hand up from here.
My screen is not up. Let me leave and join again.
Okay, all right. Okay, now let's. Any other comment, question from anybody before we move on? Okay, so let's move on to the next discussion. But as we move to the next discussion, Let's take some 3 minutes break. So we are coming back 8:15 to continue. All right. Okay, we can continue now. We want to talk about the partitioning strategies. So first we have to understand what it means by partitioning. It is briefly a process of dividing an input data set into multiple segments known as partitions. Now, each processing node, which could be a CPU, then performs an operation on the individual partition of the data set rather than the entire data set. So that is what we mean by partitioning. Divide the data set into segments. Place the segments on various storage devices. Each processing node or processor may perform operations on a particular partition. Okay, by so doing, so far as we have processes accessing various data across disk, we call it that we say that they are performing the task in parallel. So parallelism reduces the time required to retrieve relations from disk by partitioning the relations into multiple disks. There are several strategies, but even if I ask you right now that how do you divide the data across many disks? Of course, for everybody may guess or would even suggest that all we need to do is to find a way of splitting the data evenly across various disks. So we'll see the strategies that have been used to attempt to distribute the data evenly across many disks. Okay, so let us take, for instance, that we have several processes starting from processor P0 Pn-1. Similarly, we have disk as well, from disk D0 to Dn-1. Okay, and then we want to attempt to distribute some data set across the disk 0 to disk n or to disk n-1. What strategies are there that we can use to achieve this? And that is what we want to look at. But let me just ask this question. It has escaped me. I don't know whether I've added it to your assignment. The assignment that I gave you the other day to speak the project, did I ask any question on using a strategy, partitioning strategy to partition a data set? Anybody who has seen something like that on the questions? I'm sure there is. Or that the questions are not yet read, and then maybe you haven't reached there, and therefore you haven't seen it. Okay, maybe nobody took notice of it. It appears the last question or so, or the last but one.
Hello, sir.
Yes. Yes.
There is question 10.
Well, how does it read?
You asked about partition strategy, and I said there is one in the assignment.
Yes, there is one in the assignment. I was asking that you should use some partitioning strategy, number 10, to partition. So this lecture here,
yes, sir,
can give you some idea as to how you are going to do that practically. Okay, that's good. Now, having processor, n processors, and n number of disks. These are some of the strategies that we can use. Some of them are very obvious. We have horizontal partitioning that involves putting different rows into different tables. So if we have, let's say, 1 million records in a table, and then we want one disk to process it, it's going to take a lot of time, even searching to retrieve records and so forth. Why wouldn't we maybe distribute them into maybe 100,000 each? So we create 10 tables, and then we pick maybe a certain number of rows to one table, 100,000, and we put another 100,000 into another table, and so forth. So when we do things of that nature, having to move rows, set of rows or records into various tables, we refer to that partitioning strategy as horizontal partitioning. Since we can do that kind of distribution using the rows, we can also vertically partition tables. So if we have tables containing 100 columns or 100 attributes, we can choose to break it down so that 10 columns will be in one table, the next 10 columns another table. So we can get 10 tables out from one table with the data. So if the data, the total number of records in that table is, let's say, 200, when you split horizontally, you are going to find the same 200 records in each of them, because you only pull you separate it vertically, just picking the columns. So that is the vertical partitioning. This vertical partitioning can also include the concept of normalization that we were talking about the other day, that we can split a table, one table, into many tables. And some obvious ways of doing it is to create a master-slave or parent-child tables joined with primary keys, foreign keys, or we can even split two tables into two, and then they will all have one-to-one relationship. So such partitionings are referred to vertical partitioning. So if I break two tables into if I break one table into two, I can join them on one-to-one relationship, and then they now become two tables or three tables. We can assign each of the partitions to a CPU to process, or to do some changes in there and update records in there. So that is vertical partitioning. We have another method of partitioning, which we call round robin. The attempt to find a way of evenly distributing records onto various disks. This concept becomes very important, where we can use some mathematical formula to carry out the distribution. This one and the hash partitioning, we use mathematical formula. So for instance, we want to use modular arithmetic. We just do that. Let's say we have 10 disks, and we want to split the data on 10 disks, and 10 processors should process it. We can just do something simply like this. We can just say the number of disk mode 10. Then if we pick, let's say, the first record, let's say record 1, In mode 10, it will give us 1. Then we send that first record to a disk. Then record 2 in mode 10, because the number of disks are 10, or processes we are distributing them to, and then the disk are 10. Then we do the same. Then when we come to maybe the 11th record, so 11 mode 10, it will turn to 1. Then that one goes to disk 1 again, and then so forth. When we follow a pattern like this, you will notice that eventually we would have almost distributing the data evenly across the disk, because when it gets to the largest value, it will come back to start again. That's its round robin. It will come back again to the disk 1, and then so forth. Now, if I ask you to write a simple program, like I was asking, maybe database program, you write it in database, and then you run it to, I say, create 10 tables, then write a query. That one query, you click it, it will distribute the huge table that contains all the records. It will split them or partition them and distribute them across 10 tables. Shouldn't be a big deal at all. Or should it? Should it be a big deal? The way you are all quiet, it means it will be a big deal. Can anybody suggest how such a thing can be done? Are students actually with me in this class?
Yes, Prof. We are with you.
Yes, yes,
We are
Prof,
with
we are
you.
here.
So far as you are with, then let me continue.
Okay.
I have to stop asking questions. Okay. Now I hope that this method is understood, is the simplest actually. There are other types of round robin partitioning that would actually, instead of picking record 1, record 2 as the identifier attribute, we now pick a particular attribute among the attributes, and we use the value of that attribute to do the distribution across tables. So we can find let's say a hashing function, but the function should be such that it will not skew the data to a particular disk, where some disk will contain more data or records than the other. So for instance, look at this, where we have employee table. We have employee number, e-name, department number, salary, and age. We can pick one of the attributes here. Of course, if it is numeric, the better. Let's say department number. The department numbers are department 1, 2, 3, 4, 5. Let's say they have 20 departments. So we can now say that, okay, we will use the department number as our partitioning attribute. So when we take the hash function, we put the partition number in the hash function, the partition number. Then we can then say the department number in most 20. Then it gave us something, a particular record. We send it to this one. We do it up to this 20. We take the next one, so we use this one, then we distribute across all the disk. But there is a problem. Assuming that the department number is not a numeric value, but it is alphabetic or variable character, what do you think will be done so that we can carry out with the distribution? Here they are numbers, so we don't have a problem. But if department number are alphanumeric, how do we say alphanumeric in mode 10? It creates problem for us. So in situations of this nature, who can suggest what we should do? Anybody? Okay, yes. Wonder.
Sir, what about adding a new column that will have 1, 2, 3 attached to the table, like in numeric
Okay,
form?
okay. Well taken. Good suggestion, but that's not the best for what I'm looking for. Because you are saying that we can convert that numeric alphanumeric, and then say this alphanumeric represent 1, 2, 3, and then so forth. It will solve the problem anyway. But if you don't want to do that conversion, what do we do? Okay, let me tell you what we should do. What we can do is you know that in computing, computers, so to speak, represent every character in numeric form. Every character on the computer is represented eventually, internally, in numeric form. That's why we develop a lot of numbering systems and character sets and so forth. So what we can do is that we will convert the numeric, that alphabetic or variable character into maybe a number, a character set. Because even in ASCII, for instance, ASCII A, capital A is 65. So all characters have their corresponding numbers. So we can use that one to convert that variable character or alphabet into numbers. In that case, when we do something like that, we can use the modular arithmetic on it. So technically, when it happens that we convert the numbers, the alphabets within the attribute, convert them to ASCII or any numeric value, and then you can carry the modular arithmetic on it. I hope that is clear. Another simple way of distributing data or records across many tables is to just use range. We call it range partitioning. If you observe the data closely and you decide to segment the data in the table based on a particular attribute, and you can see that you can find ranges within that attribute, we can do so. Assuming it is salary that we want to partition across. We can say that those who earn less 0 to 5,000 should go to one table. Those who earn 5,001 to 10,000, another table, and so forth. So by so doing, we will have distributed the data across various tables by using range or ranges to carry out that. Okay, so invariably, I've talked about 5 simple methods that can be used to distribute data across many tables. So you will see some of the things computer science people and all technology people do. So if I'm in an environment where we will need to partition data, let's say a global company, we need to be partitioning the data and be sending them to various disks across the globe. You could write a simple computer program, and then maybe you run it, then it will loop, some kind of looping. So maybe the first loop, it will save it to disk 1, second loop, disk so and so. So we can create connection string that can connect to all the databases across the globe. Then we write a program in a loop or something like that sort. So if maybe the first loop, this one, so record 1, then it copies it to disk 1, which is somewhere. Then the next round is 2. disk tree. So if I put this, even this round robin into a loop, and then I connect to various databases, I can save just by running that simple program within a loop. I can distribute records in a large records in a particular table. I can distribute them and then send them or insert them into various disk. Okay, having said so, I would pause for a while if there is any question anybody wants to ask. And if there are no questions, we'll move to the next thing I want to talk about.
Okay, so my question is how can you give me a query, a simple query on how partition is done? Just to give me an idea.
Oh, but I've given you I've given you the mathematical function, is that not it? Like modular arithmetic that I've shown you.
I'm asking that because I want to know if the partitioning is actually creating new tables and dividing the old one, or it is doing that in the view and not in the actual tables.
Okay. We have, when we look at distributed systems, we have two ways. They all have their advantages and disadvantages. One way is physically actually carry out the distribution. Physically carry out the distribution to 10 disk, not a view, 10 disks, really actually carrying it out. We call that one materialized view. Materialized view, where we actually hard copy the data to various disks. In the distributed system environment, it has been seen to be better than the views that we write on a single database and so forth. Because if you want to write a view, if you want to write a view that we have been doing, and the view is going to be accessing records from tables located at different places, I'm afraid the bottleneck. I mean, because it's going to even connect to a number of tables located at various places, you have a problem. So when we come to distributed systems, we normally use what we call materialized views. They are not part of our discussion here, but when we come to second semester, I think your second semester you'll be doing distributed systems, and I'm the one who normally I've been teaching that course, but it can be given to any other lecturer as well. And so when we come there, we'll be talking about those sort of materialized views and all sorts of things, how views can be done, so that we can even permanently write records into various disks. So the discussion we are having here actually have to do with writing, not a view, we're actually writing to various disks. Not even just how do we call it, the same tape, the same machine, but even to various locations, writing to databases in different locations, writing to the disk, and then maybe to a particular table in many databases lying on many disks across. Once we run this once and we are done with it, we now have the data across maybe the globe or across many servers or on many disks that we want. So once we issue a command and this one runs for 30 minutes or 1 hour or 2 hours and send the data, we have the data physically across all these the globe. So this one is physical distribution of the data. That's why I asked you in the assignment that you should go look for it yourself and then write one. In your case, you may not probably be able to try it on a distributed system, but even in the same one database, let's say you have one database, you have one big table, and then you want to distribute the data to 10 disk or 5 disk. How do you do that? So you can write a query. If you want to distribute it evenly, a query, I'll put that query. If I want to do it in the database, this can also even be done even from front end by somebody clicking on submit. Okay, or back end, I can just write a query. In databases, we have looping statements. Do while something, then you pick, maybe you first connect to the database, then the first one save to table 1, table, then the next run table 2. A simple, beautiful program can do this and do the distribution for you.
Yes, sir. I've understood.
You
Thank
understood, isn't it?
Yes, sir.
Okay.
Thank
Okay.
you.
All right. Any other question?
Yes, Prof, I have a question.
Okay.
So, when it comes to the hash partitioning, and you were talking about a situation where we have maybe alphanumeric, we don't have it as numbers alone, but maybe it's letters, and then we might use ASCII to convert it. So in this case, do we just take, if it's maybe names of people, do we just consider just the first letters, like alphabetically, and then take the modular of it afterwards?
Okay, so now we can take your name, Gifty, or your full name. Then we'll go and look out for what is the, what do you call it, the ASCII representative of G. Maybe 71. We've noted down. What about I? Maybe I is 69. F. Then we sum. You see, we do some summation on this. Then it becomes a number. Then we can say mode 10. Whatever it gives us, we pick that record number, then we save it to a table. That means that record should go to a particular table. We pick another person's name, Sadiq. Then we look at the characters, the alphabets in there, we pick them, we sum. It becomes a number. Then we say in mode 10. So we begin to pick the values held by that attribute. Then we will convert, and then we find the mode of it. Gifty, can't you write a program to do this, computer program?
Hey, Prof. I'll
Oh,
try.
it's not difficult to. It's not difficult.
Okay,
All
Prof.
you need to do, because asking numbers, we already know that capital A is 65, B 66, C 67, it goes down, and then all the image dash or every symbol has a numeric representation in ASCII. So you write a program, maybe you create some array or something to be picking the appropriate representation of the alphabet. Then you collect all of them, then you sum it. It will be an interesting program, is that not it?
Yes. Thank you, Prof.
You are doing computer science, so these things you should be able to do. After a little research, you should be able to do.
Hello, Prof.
Yes.
Is the mode 10 constant, or is it because the available number of disks is 10? That's right.
No, it depends on the number of disks that you want to distribute the data onto. So here is just a mere example given that you have 10 disks. So if you want to distribute the data to 3 disks, then it should be mode 3. Mode 3.
Okay.
It will be mode 3. Any other? Okay, so let's begin the next part, segment, or subsection of the topic we have to discuss today. I told you from the beginning that today's class will be covering 2 chapters in our textbook. So we will not finish the discussion today, but in our next class we will be done with the 2 chapters. So we are now tackling content from the chapters. Okay, so the next thing we want to talk about, which we can start to a point and complete it next week, is inter-query parallelism. Then we also have intra-query parallelism. So we begin to wonder how would the processes handle queries or the operations on the data. And the other day we saw a number of, or at least some examples of queries. And in this diagram, you can see that at the top we have query parallelism, which is executing database queries in parallel. These are the things that are created that problem of concurrency things for us the other day. When things have been done, when one is doing this, another is doing that. If we don't schedule them properly, then you are going to have a problem. Okay. So this concept is more about executing multiple database queries in parallel. We have 2 main aspects of it. The first one is intra-query parallelism. That is execution of a single query in parallel by dividing the workload among various processes. It sounds quite amazing to know that one query can be worked on by several processes, because some queries are very complex, very long and complex. So if we want to leave it for one machine to complete, it will take more time. But if we give that single query, we give that single query to multiple processes to work on, we are sure to have a better throughput and performance. So consider this query over here. Select asterisk from employee and department. That they are 2 tables where employee department number is equal to department number. So here we join 2 tables. We join 2 tables. Now, what we are saying about intra-query is statement of this nature can be executed by 2 processes. One processor can take a segment of the joint. Another one will take another segment of the joint operation or of segments of the query. And then at the end of the day, they will execute independently. At the end of the day, they will put their results together and give you the answer. So this strategy normally tries to address how we will perform a joint operation of the given query in parallel using multiple processes. Now, the inter-query parallelism also focuses on, in this case, we have several lines of queries. And then we want to give the queries independently to various processes. So we can say processor, let's say the queries, let's say these queries we have. Select asterisk from employee. Select asterisk from employee where. Select furniture name from furniture table. Three statements. So we can see that, well, Processor 1 executes query 1. Processor 2 execute query 2. Processor 3 execute query 3. Then when they finish, so be it. This one is even very clear because it doesn't look like we will have problem with concurrency because they are all executing from different tables. So we won't have problem here. So if we won't even have problem here, why do we need to worry one processor to do all this? This is very short, but if you have several lines, and we give this one, we distribute the job amount, then they do it quickly. But even if they will conflict, the protocols can take, concurrency protocols can take care of them, providing in some cases that one should wait, and then so forth. So these are the two major techniques or strategies that are used when we come to parallel execution of queries. So it normally addresses how we would execute all the queries simultaneously by using parallel servers. So these are different machines. They are all executing a set of statements at the same time. Okay, having said so, I would be running off very soon. But I can wait for a moment, take some questions, then we run off. When we meet next time, we will look at some design issues having to do with parallel systems. Then we'll move on to distributed systems, actually, strategies of some types of distributed systems and so forth. And so forth. So I will leave the floor open for a moment. Then I will take your responses, attempt to address them. Then at the end, we would run off. Okay. If you don't have any questions.
Hello, Prof.
Yes.
I have a suggestion I want to make. I think we usually have a class with Professor Katriku, from 5 to 7 before your class. And he's mentioned that from next week, he won't be available, so we're doing it online.
He said so.
Yes.
Professor Katsuku said that next week he would be online.
Yes, because I think he will be out of town. I think starting next week till I think the end of December also.
Okay.
So sometimes, that's why today you realize the class was a bit dull because most of us were rushing back home to come and join the class. Exactly. So I don't know if it's possible we can also continue with this class online so that it will be easy for us to transition from one class to another.
Otherwise, you may be online on his class, then you not come to my physical.
Exactly.
Okay. Well, I think we can go by that. The reason why I was forced to make this class online today, I wanted to come physical. But the evening group lamented Saturday that, well, we were going to lose Saturday class. So if I make this one online, they can join. But interestingly, I don't think they have even joined. Is there any evening group member here?
Yeah, I'm here.
Saturday, we are here. Saturday, we are here.
Yes, sir.
Weekend, brother, we are here.
Weekend, sorry, weekend. But you are not many. Where are the rest?
Yeah, Prof, there are not many because the information came very late.
Weekend is here.
This information has been posted. This information has been posted to your class rep long ago, but he didn't inform you. I think so.
Yeah, he didn't tell us. So we saw it very late, and even though it was late, we decided to join.
Yes, we are here.
Only few of you are here.
I think, sir,
it's not good.
Some of us also had problem joining. I think it was difficult joining. For me, I joined like
Yes,
one.
yes, please. We had problem joining. They say admin will admit us. I'll be on. No one is admin.
No, that means you didn't get the correct link or what?
No, they shared another link to us too, and then I joined it again, and it was the same thing.
Okay, I see. All right, I see. Okay, so what it means is for the, what do we call it, the evening group, the Tuesday group, we can do online, but the Saturday group we can still meet since I don't know whether Professor Katriku's journey will affect the weekend as well. Is it affecting the weekend as well?
Prof, this weekend is the election.
No, I'm not talking about this weekend. I'm talking about subsequent weekends. Whether Professor Katriku's lesson or online.
We are yet to verify from him.
Okay, yeah. That's right.
Prof, according to him, he didn't talk about the weekend. He talked about 2 days. He said from next week coming.
From next week, when he was in our class, he will talk about us. Maybe when he meets them also, he will talk about theirs. Yeah, okay, so you can't assume for them.
We can assume for them.
Traveling outside the country is traveling outside the country.
If he travels outside the country, then it will affect them as well. But we wait to see how things go.
Yeah.
But the weekend, I really would want to be meeting you face to face. So most of you like the face to face than this one. This one, it makes the lecturer also talk a lot.
Yes, we like that one.
Yeah, so we will see how it will go. Okay, so please, the Saturday is the election day. I advise you. I don't want any of you to become a victim. Whoever wins, if you don't work hard on your own and create a future for yourself, fighting for somebody to go to parliament and so forth will not help you. The person can go, but you may not even get anything from it. Work and then work with your hand yourself. If you want to be a parliamentarian, go and do that one. If you are here, focus on your own. Because if something happens, they are not even going to mind you. So nobody should go and be carrying ballot papers and be running.
Yes.
Nobody should.
Thank you, Prof.
If you are a macho man, if you are a macho man and you say you want to go and carry ballot papers, it's your own problem. Or ballot boxes and so on is your own problem.
Not after undergrad and you are thinking of doing masters, and you'll be found in that category of people.
Or you can't be doing masters and go and do that kind of thing. That one, it doesn't make sense.
It doesn't speak well of that.
Yeah, it doesn't make sense at all.
Not
okay,
at
so
all.
on this note,
Prof, please, are we going to get slides?
Yes, I need to post all of them on the Sakai for you. This afternoon, I wanted to do that, but I don't know what happened. So I'll put all the materials on Sakai for you in the matter of a day. So in 24 hours from now, I'll put all of them there for you so that you can download and be reading.
Prof, you wanted to meet us, the student that you are supervising.
I've been trying to figure out the appropriate time, or which time will be appropriate.
Prof, in fact,
of course, it should be even.
Mentioned that the Saturday mentioned you wanted us to do it on Monday. So we're expecting
I thought to do it.
So I mean, I'm sure if you are able to fix any day and the time, I will discuss it at the cybersecurity page. I think we should all agree on a particular time for us to connect.
But you have classes, some groups of students have classes in the evenings. For instance, if you say Thursday, some students will be having classes on Thursday, am I right?
Thursday from 5 o'clock.
Won't Friday
Pardon?
be okay since we have a holiday?
I think that should be a good suggestion. No? It should be a good suggestion. Friday.
Yeah, Friday will not be bad at all. Friday, anytime Friday. I think we can
Even
all
Friday, I even believe that Friday there will not be campaigning by law. Is it not
Yes.
24 hours to the
They are
Yes,
bringing their
campaign?
campaign on Thursday.
So they end the campaign on when? Thursday. So those of you who even want to go and those of you even want to go and campaign, you will not have the chance to go and do that. Okay, so let's put it on Friday evening.
Okay,
Let's put it there.
Prof.
Okay,
just that I'll be traveling out of town to go and support my candidate.
Hey, Prof, you have a candidate.
I will follow you.
Hey, I
Wow.
have to go and campaign. I have to go and campaign.
Hey.
But then that one there.
Prof, advise them to vote well.
I will follow you.
Oh, you should also go and campaign somewhere.
Prof, can we get a recording
of the class?
I think he'll put it on YouTube where he has been putting it. So.
My recordings are being managed by my TA. So once you get in touch with my TA,
I never know that there's a recording about the database.